minutes. Sir? 20 minutes.
Start from here. So now we are going to discuss about some problems related to the demodulation technique, as well as we will discuss with respect to modulation also. As we have discussed square law demodulator, then synchronous detector, square loop or squaring unit demodulator. So related to that, we will solve some sort of numericals which will help you to understand the working principle of this. And one more important thing, in synchronous detection, the synchronous detection method, it is ideal. Whatever we are recovering, that is m of t, we are recovering without any sort of distortion. In ideal case we can analyze, but in practical case it is not possible. With modulating signals, some sort of noise will be there, and if there is a absence of noise, means it is cannot be possible to design. So that is one more disadvantage of the synchronous detection. First disadvantage is that practically it won't be possible, because the carrier frequency cannot be matched what we are transmitting and what at a receiver end. That is first. Second, as we have derived at the output of LPA, what we have seen, that only modulating signal is available with amplitude reduced by half. But practically it is not possible. Practically the presence of noise is also there, and it is very difficult to design this sort of detection circuit, complex circuit. Okay. So one by one we will discuss some numericals. We will discuss with respect to the square law demodulator or squaring loop demodulator, as well as coherent demodulator. So first one I am writing the question for the square law demodulator. So first one is the frequency multiplier. The frequency multiplier is a nonlinear device. Nonlinear device followed by LPF, followed by LPF, as shown in figure. Suppose the nonlinear device is an ideal square law device. Square law device. Okay. With input / output characteristics with the relation E suffix naught of t is equals to a E suffix I square of t. So this is the input output characteristics of a nonlinear device, and here we have to determine the output of a low pass filter if the input to NLD nonlinear device is an AM signal. Okay, so this is the question, and the diagram is this is my NLD nonlinear device followed by NLPF. So here I am providing EI of t. Here I am getting the output of nonlinear device, and these characteristics of a nonlinear device is given with the relation E naught of t is equals to a EI of square of t. So this is the input, this is the output of nonlinear device, which is followed by a low pass filter, and we have to determine what is the output available at the low pass filter. And input, one more hint is given, determine the output of an LPF if the input to the nonlinear device is an AM signal. Now here the AM signal you can write so EI of t is my AM signal. So this is the first hint is given. So that means this problem is related to the square law demodulator. NLD is a square law demodulator as it is given. Suppose the nonlinear device is an ideal square law device. So indirectly it is given nonlinear device will act in a principle of square law demodulator followed by a low pass filter. So here first hint is given as AM signal. So here I will write AC 1 plus m of t into Ka cos omega ct. So this is my AM signal. Now this AM signal is given to this nonlinear device. Now this nonlinear device characteristics, input and output characteristics is E naught of t is equals to A into EI square of t. So here I will write E naught of t is equals to A EI square of t. So now what we have to do? We have to substitute this equation here so that we will get the output characteristics. So so it is AC 1 plus Ka m of t whole into cos omega ct whole square. Now you need to expand this relation. Again we have to expand this. Again we have to identify DC component, sideband component, harmonic component and modulating signal component. So if I will expand this, I will get AC square into cos square omega ct and expand this value 1 plus Ka square m square of t plus 2 Ka m of t. Done. This is the expansion. Now you need to expand this whole part into certain components. So first component is with respect to 1 A into AC square cos square omega ct. So this is the first part. Second, multiply this with respect to A square. So it is AC square cos square omega ct into K square m square of t. So this is the second part. And the third part is AC square cos square omega ct into twice of Ka m of t. Done. So these are the three components which will be at the output of this particular NLD, means nonlinear device. Now this is the output of a nonlinear device through which we can identify the output of LPF and we can decide how much efficient this particular device. Okay, how we will write all these things? Let's see step by step. So E naught of T, output of energy. So first is A into AC square into cos square omega C plus second one is the harmonic component, means I can write A into AC square into K square into N square of T whole into expand this value, means 1 plus cos 2 omega Ct whole divided by 2. This is the second part. Third part is A into AC square into 2 Ka m of T. Again there is a cos 2 omega Ct, 1 plus cos 2 omega Ct whole divided by 2. Like this I can write. Similarly for this cos 2 omega Ct also you can write 1 plus cos 2 omega Ct divided by 2. In which one DC component, one harmonic component will be there. Similarly here A into AC square K square M square of T divided by 2, one component is available and one with respect to the harmonic component is available. Similarly, for this component also A into AC square 2K M of T divided by 2, one component, harmonic component is another component. Now when this E naught of T is passed through an LPL, so output of LPL. So output of LPL is centered to the modulating frequency FM. So let us consider the output of LPL is X of T. This component will be suppressed, DC component suppressed, higher carrier frequency is also suppressed. So here we will get A into AC square into K square into M square of T whole divided by 2. This is the first function here we get. And next is the harmonic component, again it is suppressed, plus next with respect to M of T and divided by 2, so it is A into AC square 2Ka M of T whole divided by 2. These two to get cancelled out. Now this equation is quite similar to the equation what I have discussed while discussing the signal to noise. Here you can see it is only the presence of M of T. So you can say this is the presence of signal. And this is the presence of M square of T which will contribute as an act of noise. As a noise. So this is my signal power, this is my noise power, and then I can determine the output of LPF is this one. These are the two components at the output of LPF. Now we need to decide whether this square law demodulator is good or not. Means it depends upon that efficiency principle. So what I will do, I will take again the signal to noise ratio and I will check whether it is greater than 1 or less than 1. For example, if I am extracting the modulating signal, so modulating signal can be extracted with the analogy if my signal to noise ratio is greater than 1. If signal to noise ratio is greater than 1 means your signal power is this, I will write A into AC square into Ka M of T, and the noise component is A into AC square into K square M square of T divided by 2. So if I will solve this, I will get twice of Ka M of T. So twice divided by Ka into M of T. Now this is nothing but 2 divided by modulation index which must be greater than 1. So this indicates that therefore Ma is very less than 2. Let us consider for this case, let Ma is equals to 1. It is less than 2 means it is 1. Let us consider. So if it is 1, the efficiency as we know, we had a relation Ma square plus 2 plus Ma square into 100. If I will substitute 1, we will get 100 divided by 3, that is 2. 33.33%. That means my square law demodulator is not so efficient. It is only 33% of efficiency, means only we are recovering the modulating signal only 33%, but rest of the power is wasted only to delivering this or the suppressing the carrier component, which is unnecessarily done. Only 33% of information we can extract, not the complete 100%. Okay, so this is the one derivation according to the given numerical. Okay, so next one we will see. One more question we will discuss. And then we will find out. So one more question. As per the given figure, determine the output if input signal is an AM signal. Okay, and the figure is so here we are providing the input as AM signal, S suffix AM. The first block is square unit. This question is related to the square loop demodulator or square unit demodulator. After that, it passed through an LPR and then it passed through the square loop. Means whatever the signal we will get at the output of LPR, simply it will square root of it, and then we have to determine the output. Okay, so here we will get S square of t. If I am providing S AM of t, we will get S square of t. Pass those values to the low pass filter and then pass that value through the square root, and then you can determine the output. So step by step again we will see how to correlate this particular function. So first AM signal. This is the solution. AM signal we can write AC 1 plus KA M of t cos omega ct. So this is my input. Then output of square unit. Output of square unit. Let us consider this is y1 of t. So y1 of t is s square of t. S square of t means squaring this component. I will get AC square cos square omega ct 1 plus m of t whole square. Done. Now we need to expand this relation. If I am expanding this relation, I will get AC square cos square omega ct whole into 1 plus k square m square of t plus twice of ka m of t. Then again expand it. So it is first component is AC square cos square omega c with 1. Then with respect to this, it is AC square k square m square of t cos square omega c. Done. Plus next component is AC square, this is twice AC square ka m of t cos square omega ct. Okay, so these are the components. Now you need to expand this cos square omega ct, and you need to pass this component through the low pass filter. So if I am expanding this, it will consist of a DC component and a harmonic component, which will be suppressed by low pass filter. So here directly I am writing output of low pass filter. So here you can see, here it is y2 of t. Let us consider. So y2 of t, we will get this cos square omega ct, as we have derived for earlier problem, 1 plus cos 2 omega ct divided by 2, we will get AC square k square m square of t whole divided by 2 into 1, and then cos 2 omega ct will be there, that will be suppressed. Plus here also 1 plus cos 2 omega ct divided by 2. So here we will get AC square ka m of t. Okay. Now if you solve this AC square and k square, it is nothing but 1. We will get m square of t whole divided by 2 plus AC m of t. So this is the output what we are getting at the output of an LPF. So this output of an LPF, you can see this AC square and this k square, it is 1, because since AC square and k square we are multiplying, and then m square of t, as we know that this ka is equals to 1 by AC. So here I have cancelled. So resultant is m square of t by 2, and then AC into m of t. Now this is the output of an LPF. Now this output must need to be entered through a square root. Okay. Now in this case you can see, if I will expand this component, we can consider Vm cos omega m t, Vm by 2, then harmonic component is available, and then AC into m of t. If harmonic component is available, it will act as a contribution of noise. So we need to suppress this contribution of noise. So whatever the output of the square root, let us consider it is y3 of t. Y3 of t, we will get root over of AC into m of t. So this will be the output of this square root. Why we are not considering this one? Because if I will expand this, it consists of Vm by 2 and Vm by 2 cos 2 omega mt. So that is a harmonic component. This low pass filter will identify this component as a noise. So our information is only AC into m of t. You can see that AC square Ka into m of t, or if you take the square root of this, you will get AC root over of Ka into m of t, or directly you can write root over of AC into m of t. So this is the output of this square root. So this is one sort of numerical related to the squaring unit. Okay. Okay. Thank you.